Alright, for the energy level diagram in Born-Haber cycle, okay, so we will need the energy axis. Okay, so here we have energy, right, and then we are going to start with enthalpy of formation, which is this one is 0, indicates our elements. Okay, so here is our ionic solid compound, the one most of ionic solid compound, which is in this case is the lithium chloride solid. Okay, so the lithium chloride solid is comes from the elements which is lithium, okay, and also half of chlorine gas, right? So here is the enthalpy of formation. Since the value of the enthalpy of formation here is negative, so our arrow should go downward. Okay, so negative value, negative sign, the arrow will goes downward, while for the positive sign, the arrow will goes upward. Okay, so here let's label it as the enthalpy of formation of lithium chloride, which is negative 409 kilojoule. So seems like our energy cycle diagram. Okay, just put it in kilojoules units. And then after that, we are going to change our elements into gases atom, but we are going to do this one by one. Okay, so we change the lithium first, okay, and then you can change the chlorine gas into chlorine gas atom, or you can change the lithium solid into lithium gas atom, and then lithium gas atom into lithium gas ion. Okay, so I'll do the lithium part first until we get from solid into its gaseous ion. So you can do either way. You want to do the atomization first for both, and then start with ionization energy for lithium and then electron affinity of chlorine, or you want to settle the lithium until its gaseous ion, and then you start with the chlorine until its gaseous ion. So for the atomization of lithium, if you notice here, okay, I have lithium solid to lithium gas. But then for my chlorine, I just let it stay as it is. So I didn't change anything for my chlorine. Okay, so this enthalpy here is only for the atomization of lithium. So since here for the atomization of lithium, it just need energy 159 kilojoules per mole. So the distance between this and the elements and also our gaseous atom of lithium here is just a small distance. Okay, it indicates uh, the energy needed, okay, is only 159 kilojoules. Okay, so the bigger the value, okay, the longer the arrows that you got here. Okay, so since here is positive value, so the arrows will go upward. So next, I change lithium gas atom into lithium gas ion. So this is the ionization energy of lithium. Okay, so since the value is bigger than positive 159 kilojoule, so if you notice here, my arrow got longer. Okay, so the distance between these two are bigger. So again, I didn't change my chlorine gas. My chlorine gas stay half of Cl2 gas. Okay. So after I get my ions, okay, so since the formation of the lithium chloride is from Li plus gas ion and Cl minus gas ion, so since I already got my Li plus gas ion, so it's done for lithium. So now I will change my chlorine gas into chlorine gas ion. So first it will goes to the atomization at the enthalpy of atomization of chlorine. So I will convert my Cl2 gas into Cl gas. So since for the atomization of chlorine only need 121 kilojoules, okay, so the arrow here is shorter than 520 kilojoules. And then after that, okay, I will convert my chlorine gas atom into chlorine gas ion, which is the electron affinity of chlorine. So since the enthalpy change here is in negative value, so the arrows will goes downward. So I'll just make this line here a little bit longer. Alright, so I will make it a little bit longer. Okay, so that I can put the enthalpy change here, the arrows in a downward position. Okay, so here is for chlorine. Okay, it will goes downward. Okay, so the delta H here, I'll label it as delta H4 negative 364 kilojoules. Okay, so if you notice here, the distance become bigger because the value here is 300 something. So the gaseous ion to the ionic solid is the lattice energy. So the lattice energy for the formation of the bond is negative isothermic process. So the arrows will go downward. Okay, so this one is the lattice energy that we want to find its value. Okay, and then again by applying Hess's law, so we know that the enthalpy of formation is equals to delta H1 plus delta H2 plus delta H3 plus delta H4 plus the lattice energy.